See?
Okay. So let's start. Welcome, everyone. Thank you for coming. Well, it's a pleasure to introduce our speaker today, Eloise Comte. Welcome. Eloise did her PhD in 2017 in the University of La Rochelle. She has a PhD in applied mathematics. She's not a physicist. We'll see it today. And after that, she spent several years of postdoc in La Rochelle University and also in the INRIA. It's the French National Research Institute for Digital Science and Technology in Nancy.
Yeah.
And after that, she got a position as chargé de recherche in the INRAE, which is the French National Research Institute for Agriculture, Food and Environment, where she is, she's mathematically working on several problems of control, and that's what she is going to tell us today about optimal control applied to lake eutrophication. Okay, so please go ahead.
Yeah. So thank you very much. So as I am here for 6 months, I will just take a minute for present you my institute and my lab before talking about lake eutrophication. So INRAE. So this is the French National Research Institute for Agriculture, Food and Environment. So this is a big institute. We have 18 centers INRAE in France, and I work here in Clermont-Ferrand, so in the center of France. And I am part, so this is where is Clermont-Ferrand. And I am part of the Department of Mathematics and Digital Technologies, and especially at Complex Systems Lab. So complex system labs, we are few permanent researchers. We are only 7. So the head of the list is Jean-Denis Mathias. I also mentioned Guillaume Defiant because I know that some people here knows Guillaume. So Guillaume is part of my lab. So my research profile, I just give you some keywords. So I made mathematical modeling of biological, environmental, or physical phenomena. And I do some theoretical analysis and then numerical analysis and numerical simulations. And my 2 principal tools, which are my 2 specialties, are optimal control problem and partial differential equations. And my applications are mainly focused on water pollution. So I've worked on groundwater pollution from agricultural activities, and I work actually on a big project of lake eutrophication that I will talk to you just now. So just before present you the context of lake eutrophication, I will just give you a focus on optimal control problem, because I don't know if everybody is okay with that concept, and it is the big concept of the presentation. So I take just 1 minute. So optimal control problem, generally, what we want to do is a maximization or minimization, as you want. So you want to find the optimal control variable. So the optimal control variable is u. You want to find it in order to maximize the functional. And the functional depends on the optimal control variable, u, and depend also of a state variable, c. And this maximization is subject to a state model, which gives the dynamics of the state variable. But this dynamics depends also of the control variable u. Okay? So this is an optimal control problem. So if I give you an example in order to understand where there is some difficulties on this problem, I'll give you an example of a work of groundwater pollution from agricultural activities. I present you this example because it's combining economic and environmental approaches, and it will be the same idea for the lake eutrophication. So you have a context. In this context, you have agricultural crops when they are fertilizer spreading, but unfortunately, there is a part of the fertilizer which is non-consumed by the plants. It is leached into the underground and transported through a water captation well. So the water here is polluted. So before drink it, you have to clean it. And to clean it, there is a financial cost. So the optimal control problem here is to find a trade-off. So this is the maximization that we want to do, a trade-off between agricultural benefits, which has to be high as possible, and which depend on the control variable, which is the fertilizer spreading. So the U here is the fertilizer spreading, minus the environmental damages. So this is what happened here. And the environmental damages will depend on the concentration of pollutants that you will find here in the water captation well. And we do it by taking into account what happened into the underground. So we're taking into account the pollutant dynamics into the underground. So the dynamics here, this is what happened here. So the difficulties that we have in this kind of optimal control problem, and this will be the difficulties that we have for lake eutrophication, is that there is strong couplings in the model, because in optimal control problem, you want to find the optimal variable control, the U living in a functional that depend on U and on C. So you have to find C, but to find C, you have to solve the state model, which depend on C and on U, and this is the U that you want to find. So there are strong couplings in every optimal control problem, and this is the main difficulty that we will have in mathematical analysis. There are also several time and space scales that could be appears, and to deal with it, we have appropriate techniques in mathematical analysis. So now I will present you the lake eutrophication problem. So this is a big project that I have, and this is a collaboration with Catherine Choquet, which work in La Rochelle University. So what is lake eutrophication? You have a lake, but in front of the lake, you have watersheds, and in this watershed, you have agricultural activities, industrial activities, and these activities lead large presence of nutrients. The nutrients, which is interesting here, is the phosphorus. And these nutrients are drained by the river from the watershed through a lake. And when there is an accumulation of nutrients in the lake, it leads to the growth of algae, and specifically of cyanobacteria. So this is this accumulation of nutrients leading to the proliferation of cyanobacteria that we call eutrophication. And this is a problem because cyanobacteria are bad for the biodiversity of the lake. So this is an ecological issue, but you have also socioeconomic issues because cyanobacteria can produce cyanotoxins, which are dangerous for human and animal health. And if you have too much cyanobacteria in a lake, the lake is closed. You cannot swim, you cannot have some fishing activities, you cannot use a boat. So it leads to economic issues because people don't come to the lakes, they don't come to the restaurants, to the camping. So this is a big problem for the economic activity for the municipality around the lake. So one of the solutions is to build a wetlands just before the entrance of the lake, which enables the retention of the nutrients. But unfortunately, this is not sufficient to stop the accumulation of nutrients and choose the eutrophication. So we will focus on this problem, which is ecological and socio-economic. Yes.
Can remove the nutrients or not? Sorry, the rotation is only delayed, or?
No. Actually, it's the wetland is it's some plants that can absorb nutrients, but after you have to cure the wetlands, and it costs yes. Yeah. So for the state of the art of this kind of problem, in a mathematical point of view, there is a very classical model, which is the model of Carpenter, which is a ordinary differential equation model. So it only takes it only depends on time. But what you can see here is that what it is interesting for us is to have a swimming area open. But the lake can be very, very large. And the biologists have proved that the cyanobacteria proliferation is heterogeneous. So you can have some cyanobacteria here, but not here. So the space is very important for us in order to control just some areas. And to do this, we need partial differential equations model in order to have space and time. So Brockings, Papadeas, and Grass has done these PDEs models. So they take into account the diffusion process that we have in the lake, and it is what we are interested about. They also introduce optimal control problem. So that's exactly what I have explained to you before. They find a trade-off. So the trade-off is between agricultural benefits, what happened at the watershed, so the polluters, so industrial, agricultural benefits, and the damages for lake users, so people who cannot swim, who cannot have some fisheries activities. They introduce the control. So the control is the incoming phosphorus load from the watershed, and this is subjected to the dynamic of the phosphorus stocks, so what happened in the lake. So their model is the following. So this is the same color code. So the incoming phosphorus load, this is the control variable. So they want to find the optimal incoming phosphorus load in order to maximize the benefits, the agricultural benefits, which depend on the incoming phosphorus load, minus the damages for the lake user, and the damages depend on the stock phosphorus that you have in the lake. Okay, so this is the functional that we want to maximize. Here there is an exponential minus rho t. So rho, this is the social discount rate. This is very classical in this kind of economic functional. It enables to compare different costs and benefits that occurs at different times. And here, so you can choose it between 0 and 1, and it can give a more important weight for the actual generation. Okay, so this is the maximization that we have, and this is subjected to the phosphorus stocks dynamics into the lake. So you have this partial differential equation with a diffusion term. Here, this is the loss rate, the mortality, if you want. And here, this is the sedimentation, so the internal phosphorus load that you can have. And here, this is the incoming phosphorus load. Okay, so initial condition and boundary condition. So Brockings, Papadeas choose periodic conditions. They are in a 1D model. And Grass, this is a Newman homogeneous boundary condition in 2D. So I start from this model, and I will make some contribution to this model. So that's why I present you this model in order to explain each term that I will add. So to do this, just take a look on the lake. So we only work on the lake and on its boundaries. So I will distinguish three parts of the boundary. So I will distinguish the large boundary here, gamma in black, with the boundary at the entrance, so where the river discharges into the lake. So gamma in here in red, this is the entry of the lake. So this is where the phosphorus load comes into the lake. And here in orange, in gamma out, this is the exit of the lake. Okay. So I start from the model of the literature, and I will explain to you the contributions that I made for the modeling. So first of all, I remove here the incoming phosphorus load, which is in the entire PDE. I will explain to you in a few minutes why. The first contribution is that I add a convection term. So this is this divergence of velocity V and S. So this convection term enables to have a velocity in the lake, V. So you can choose velocity equals 0, it's the same, but you can choose a velocity positive, and in certain type of lakes, this is interesting to have this. So now you have a convection diffusion equation. The most important contribution is that I take into account the cyanobacteria concentration dynamics. So remember, the eutrophication is the accumulation of nutrient, phosphorus, leads to a proliferation of cyanobacteria. But from now, in the literature of mathematical models, they take into account also the phosphorus. Here, I take into account the phosphorus and the cyanobacteria. Okay, so to do this, I have this PDEs for the cyanobacteria concentration with the divergence of VC. So this is the convecting term, the diffusion term, the mortality or loss rate. And here, this is the reaction term enables to link, to coupled the two PDEs. So this term is called the monotherm. This is a term made by the biologists. It's like if you have some phosphorus stocks, the cyanobacteria eat the phosphorus and growth with that. Okay, so this is the biggest contribution that we have in this kind of model, because to the best of our knowledge, we haven't seen complete partial differential equations for cyanobacteria and phosphorus. So, as I have the cyanobacteria dynamics, I can change the damages for the lake user here. Remember, before the damages depending on the stock phosphorus, but now I have the cyanobacteria concentration. And in reality, when you are in a lake, the measurements that I have that are made for saying the water is good, you can swim or not, it's not on the stock phosphorus. The measurements are made on the cyanobacteria concentration. So this is very more realistic to do this, because in reality, this is the cyanobacteria concentration which is measured. So I introduced also nonlinearities in the reaction term and in the mortality terms. So now we can have some mortality terms which are nonlinear depending on the variables. So it is more difficult. And I made some different boundary conditions. So remember, we have in the literature a periodic boundary condition or Newman condition, which are not very realistic. So I will explain to you part by part what are these conditions. So remember, gamma, this is the large part of the H, gamma in, this is the entrance, and gamma out, this is the exit. So what we have in gamma here, this is homogeneous Newman condition on the total flow. It means that there is no output flow. So this is an impermeability condition. So why this is not just a gradient here? This is because I have introduced a convective term. So I have introduced a velocity. So the condition is on the total flow. Okay. So what happened here at the boundary at the entrance? For the cyanobacteria, we have the same homogeneous Newman conditions. So no outflow, no flow outputs. But what we have for the stock phosphorus is that we say that at the entrance of the lake, the stock phosphorus is known and it's equal to the incoming phosphorus load. So remember, this incoming phosphorus load, it was in the entire PDEs previously. And I say to you, I remove it because you cannot make measurements of the incoming phosphorus load on the total lake. And the incoming is just incoming here at the entrance where the river discharge. So realistically, it's more interesting to have the incoming phosphorus load just here controlled at the entrance. So that's why I remove it from the PDE and I put in on this Dirichlet condition. So this Dirichlet condition, it's called a Dirichlet boundary control because the control is not in the entire PDE. It's only on a part of the H of the boundary. Okay. And what happened at the exit here? We have what we call non-homogeneous Robin condition of the total flow. So Robin condition, I don't know if you are, if everybody is okay with that, but if you are this R, which is equal to 0, it's like if you have homogeneous Robin condition, you have two possibilities. If little r tends to 0, you have just this and this like before, homogeneous Newman. But if it tends to 0, it's like Dirichlet knowing at the boundary. But here we are in the case with we have big R difference to 0, so non-homogeneous Robin. So two different types. If little r tends to 0, it's like non-homogeneous Newman on the total flow, knowing equals to big R. But if little r tends to infinity, you take this condition, you divide it by little r, and you have this. So this terms tends to 0, this terms also. So this is like we are, if you have S tends to 0. So what does it mean? It means that at the exit, you have a filter, And this filter is equals to big R divided by little r. This is the filter. And this filter is infinitely powerful, but infinitely thin on the exit. So it brings the value S, or this is exactly the same for C, to the value of the filter, big R divided by little r. Okay, so what does it mean, this non-homogeneous Robin condition? It means that at the exit, a part of the pollution can exit according to this filter, but not a large part because the filter is very thin. Okay, so that's what happened in the reality because the lake has an exit. So this is more interesting than the previous condition, which was, there is an echo. No problem. Okay. Okay, so that's for the boundary condition. So as I mentioned, we have this directly control condition. So we change the control that we find. So the control is only on the gamma in, so at the entrance. And as we have that this is not an optimal, a classical optimal control problem. This is what we call a Dirichlet boundary control problem. Okay, so this little bit different. And the last contribution is that the model is valid in 3 dimensions. And previously it was only on 1 and 2 dimensions. So here we are in 3D. So that's the model that we have for lake eutrophication. And according to this model, I will present you the mathematical results that we have. So first of all, just some yes. For now it's constant. Yes. Yes. Now it's constant. We would like to try to make the velocity of a variable, but from now it's difficult. We have enough difficulties now.
Something that you the velocity that you just need to so that the problem is
yes, from now, yeah, from now it's yes.
So how it means the divergence terms because the velocity is also related to the flux and the boundary.
Yeah. Yeah.
So the same velocity everywhere.
Yes, from now, yes.
So you have in the boundary condition, you have like a flux related to the velocity, right?
Yes. Yeah.
And then the same, and it's the divergence of the same velocities that is related to convection.
Is the same velocity here or of here? Yeah. That's the question? Yeah. Yeah. Yes. Yes. This is just to introduce the convection. And the convection is this term. But if you introduce convection, you introduce velocity. Okay. So the assumption, so the control variable, P, lives in this set. So P is L inf T, and P is bounded. Okay, so it's positive, and you cannot have an expression of P. So this is very classical. So now assumptions for the benefits function. So the benefits function depend on time. This is classical because time dependence may, for instance, be induced by seasonality of the activities. So the benefits cannot be the same in January or in August. It depends on space because the loaders can have different locations on the watershed. So the phosphorus load can load it at several parts of the lakeshore. And it depends on the phosphorus load on the lakeshore. Okay. So mathematically, what we need is that this functional is bounded, concave, and upper semi-continuous with regard to the phosphorus load. What we have for the damages, so the damages also depend on time. As you can see, the blooms of cyanobacteria are more present in summer. So it's reasonable to assume that the damages are more important in summer than in winter. Depend on space, naturally, and on cyanobacteria concentration. So what we need for the mathematical point of view is that D is bounded and piecewise continuous with regard to the cyanobacteria. So now the assumption that I need for the other part is the following. So I've introduced the velocity. So I have some incompressible water assumption on the velocity. So divergence of velocity equals 0, which is very classical. And I introduce also a condition on big R. So big R, remember, it appears on the Robin condition on the filter that we have at the exit. So what does it mean to have that? The understanding is that if you have the outflow rate at the exit very large, this is not sufficient to drain the lake of its pollution. Okay, so that's we have a filter, but you cannot drain the lake of its pollution because there is no problem if it's the case. And in reality, this is not the case. Pollution can be exit, but not sufficiently to drain the lake. The third condition is on the monofunction. So remember, monofunction is the reaction term between cyanobacteria and phosphorus, so, and with the mortality rate. So what does it mean to have this condition? It means that if the cyanobacteria concentration is very large, then the cyano mortality, the loss rates, will be greater than the birth rates. It means that you cannot have an explosion of cyanobacteria in the lake. If the cyanobacteria concentration is very large, then the mortality will be greater than the birth rates. And this is something with the biologist agrees with this assumption. Okay. We have quietly the same assumption for the stock phosphorus. So if we reach a maximal stock of phosphor, the loss rate becomes greater than the discharge rate. So this is the sedimentation. So this is exactly the same. You cannot have an explosion of stock phosphorus. And also biologists agree with this. And the two last...
The concentration of food is too large, there will be another mechanical or physical process like sedimentation that will remove the phosphorus.
If it's... Yeah, yes. And the two other assumptions are for the mortality rate, which is non-negative and bounding, and the discharge, which is non-negative function. This is the 6 assumptions that we need, and they are very realistic. Okay, we try our best. So, so as I mentioned, we are not in a classical optimal control problem. We are in a Dirichlet boundary optimal control problem because the control is on the boundary. So classically, for theoretical and numerical analysis, what we do is a lifting of the model in order to shift the control from the boundary to the entire PDE. As I mentioned, it is more realistic for us to have this Dirichlet boundary control problem because we can measure the phosphorus load at the interest, but not in the entire lake. But for mathematical analysis, we made the shifting. So we made the lifting problem. So the construction of the lifting problem is guided by 2 concerns. So we will follow them. So we have to ensure that the lifting operator is inversible. So we can actually derive an equivalent form from the original control problem. And the second is that we are choosing only one assumption on P, namely the realistic assumption stating that there is no blow up of P. So I will not enter in the details for the construction of the shifting model, but we introduced a lifting operator. And with this lifting operator, we are able to construct the shifting problem. So we use the H problem and its elliptic counterparts and this lifting operator. If you want some details, we can discuss later, but I'm not sure this is very interesting to take time on this. Yes. The lifting operator, we need it. We have a Dirichlet optimal control problem. This means that the control variable is on a part of the boundary. This is realistic, okay? but mathematically, it is very difficult to have some mathematical results on this. So for the mathematical part, we need the control in the entire PDE. Okay? And to shift the control from the boundary to the entire PDE, we used a lifting operator. And this will lead to a lifted problem, which is equivalent to the Dirichlet boundary control problem. But you will see the lifting problem is this, and you can see up here the P in the PDEs, but it's not just plus P as before, because plus P, it means that the phosphorus load is the entire lake, and this is not realistic. No, here it's divergence of velocity P because of the constriction of our problem. And you can see here on the boundary at the entrance, there is no P. Okay, so this is the lifted problem where the control variable is on the entire PDE and not in the boundary. Okay, and this problem is equivalent to the Dirichlet boundary control problem that we have. Okay, so mathematically we use this, but physically it is equivalent to the Dirichlet boundary control problem with the control only at the entrance of the lake. Okay, so for biologists, for numerical simulations, etc.
If you were to consider that you have a Dirichlet boundary condition with a fixed concentration, then you simulate a model, you get a given distribution of concentration across the lake. The stationary solution of that problem is the stationary solution is the same is the possible distributed along along the lake. You that concentration at the end. Yes,
you can use the model that you want. This one, if it's better for you for the numerical simulation, because I don't know, this term is better, you use it. If it's better to use the Dirichlet boundary control problem, this is equivalent.
That is how we. I said that maybe it's possible for, let's say, a stationary solution.
Yeah.
But
yes.
In general, is also the case. So this is the same.
In general, no. You need to have the good lifting operator. Yeah. You need the good lifting operator, and depending on the lifting operator, you cannot. This model is quite good because this is not a complicated term, but depending on the lifting operator and the type of the equation, maybe it will be difficult to. The lifting model will be difficult. Yeah.
What guarantees that even with the condition at the end, you have some swirling flow in the lake and that is stationary? The condition guarantees. You're assuming that you have, you have a certain profile stationary. What can guarantee that you have oscillating, let's say?
The Dirichlet condition? Physically? Oh.
It means hydrodynamics. She had no other dynamics. She just took a constant velocity, but not including negative equation. Yeah. Is that right?
I think this was the question. Yeah.
In that case, you cannot apply this technique because you have a turbulent flow. That concentration in the lake will not correspond to it.
Okay. So as I mentioned, this model is equivalent. So for our mathematical results, we will use it because this is less difficult, not more easy. So the result that we have, it's maximum principles on the two-state variables. So maximum principles are answered for the stock phosphorus, which are positive. So I don't make the prove it. This is very, yeah. So we need assumption 1 and 2. We have also the positivity of the concentration of cyanobacteria. And we have that the concentration of cyanobacteria is inferior to a Cmax. So this is bounded. And this is the same for the stock phosphorus. So you see that assumptions that I have shown you before are needed here. So the maximum principles are are okay here. So this is very important for us for this type of parabolic partial differential equations. So now I will present you the aim of this model is to prove the existence of an optimal control solution. Okay, but in optimal control problem, as I mentioned, there is a lot of coupling. So we have to just focus on the state models, on the PDEs, and then we can work on the entire optimal control problem. So now I will focus just on the state models, so the coupled PDEs for cyanobacteria and phosphorus. So I have existence, uniqueness, and stability of the solution. So this proposition answers the uniqueness. I don't prove it here. This is classical. But we have this theorem that answers the well-posedness, so existence, uniqueness of the solution for the state model. So it means that we have a solution, so stock phosphorus and concentration of cyanobacteria living in L2H1 cap L50 L2, the maximum principles, which is satisfied. So for proving this theorem, this is classical, the existence of a weak solution for this type of nonlinear parabolic problem, we use the Feido-Galerkin method. For the energy estimates, this is the tricks that we use for maximum principles that I made before. And as mentioned, non-homogeneous directly boundary condition, we treat it with the lifting that we have. So we have also stability results. I show you just here the convergence that we have because it will be we will use it later. So we have strong convergence for S and C, and also strong convergence for the gradient, and also for the gradient on the boundary. So now this is the main scope. So this is the theorem that answers the existence of a global solution for the optimal control problem. Okay, so for the maximization subjected to the state model. So there exists a global solution, P start, S start, and C start to the problem, with P start belongs to the set E and properties that I have presented you before that are given for S start and C start. So just here, the notation start actually mean optimal in optimal control problems. So it means that this is the optimal solution. So I will finish with a proof of this theorem quickly. So we have this set. So this is the functional J, depending on P and C that we want to maximize. P belongs to E and C and S satisfying the state model. This set is non-empty. And according to the smoothness assumptions that I have made for B and D, remember they are bounded. D is continuous and B is upper continuous. So we have, this is bounded. So there exists a supremum. So this supremum, I denoted it J start. So it remains to prove that J start is the greatest element of the set. Okay. So by definition of the supremum, there exists a sequence Pn associated with a solution SnCn of the state problem, so that we have this limit of J of Pn Cn, which is equal to the supremum J starts. Okay. But what we can say also is that there exists a subsequence of Pn. It is not renamed for convenience, which is associated to a function PL, and we have this weakly start convergence of Pn through PL in L-infinity. So I will associate to PL the solution SL and CL, and according to the stability convergence that I have before, we are, remember I have a strong convergence for S, C, and for the gradient. I can pass to the limit with this solution CL, SL, and this solution satisfied the state model. This is just the state model passing to the limits with solution SL and CL. So I am able to do this because I have the strong convergence proved in stability. So what I have done here is that I have a solution SLCL and I have passed to the limit in the state model. But we look at the entire optimal control problem. So what I have to do now is to pass to the limit in the optimization, so in the functional J. So that's what I am doing now. So to pass to the limits, I have to use the smoothness assumed for D and the Lebesgue convergence theorem. And I am able to pass to the limit and say that the limit of D of Cn is equal to D of Cl. I can do this because I have smoothness assumed for D and Lebesgue convergence. It is a little bit more complicated for the benefits for B. So I use that I have a weakly convergence for Pn through Pl in L2. And as B is concave and semi-continuous, I can use a lower semi-continuity argument, which is very important here, because it enables to say that B of Pl is superior to the limit sup of B of Pn. So I don't know if you are, if it's okay for you, but we can use it because of the assumption of B, which is concave and semi-continuous. So this lower semi-continuity argument is very important. And with these two, we can conclude that G start, which was our definition of supremum, which was limit of G of P and Cn, is inferior to the B of PL minus D of Cl, which is G of PL Cl. And as this is a supremum, it implies that G start equals to G of PL Cl. So our theorem is proved because we have proved that the solution PL Cl is the optimal solution P start, C start. So we have passed to the limit in the state model and in the optimization. So it's very important to have this because we answer that the optimal control problem that we have as a solution. Okay. So for the conclusion, what we have here is a strong modeling with coupled stock phosphorus and cyanobacteria concentration, reaction diffusion convection equation, because we have introduced the convection, and of course a directly boundary optimal control problem with a phosphorus load not in the entire lake, but just at the entrance. We have results for the state model, so for the coupled PDEs, existence, uniqueness, and stability results. And of course, the main results, which is the existence of a global solution for the optimal control problem. So upcoming for this work, Pontryagin optimality conditions, which are conditions needed for the algorithm for numerical simulation. This is very classical in optimal control problem. And taking into account the temperature and the wine and bathymetry, because these weather conditions are very important for the proliferation of cyanobacteria. So in September, if everything is okay, I will have a PhD student to take into account this temperature, wine bathymetry, and continue this work on this problem and have some numerical simulations. So thank you for your attention.
Well, thank you very much. Questions? Emilia.
Have you worked on some specific form of the benefit and the cost functions? I'm curious on what will be in specific in real cases. What things will they depend on? Yeah. What will be their form?
Yeah. From now, no. This is just a mathematical point of view, but we have discussed with biologists and with people around the lake, and we think that we can find some functions that we can test for numerical simulations. But now this is just a mathematical point of view. That's why we try to make less assumption as possible and more realistic assumptions. But from now, we have not tried.
So something like, for instance, for the benefits, for instance, so the benefits increases with the phosphorus, no? Because the more you fertilize, no? And then it has a maximum.
Yes, there is maximum. This is concave, so yeah.
At a certain point, you put too much fertilizer, the plants do not grow more,
yes,
and then you
exactly.
lose. No? So
if you put a lot of fertilizer, the plant dies if there is too much. So yes.
So there is a maximum there.
Yeah.
From the benefit point of view.
Yes.
But then you have the cost. You have another shape, no?
Yeah.
More questions?
Well, so I have two questions. So we had Bert Kappen here, I don't know, a few weeks ago, who's also an optimal control person. And he was saying that it is usually very, very difficult to get the optimal control, even for very simple non-spatial problems, if the cost function isn't quadratic and the problem isn't very simple. So, but I didn't get how, so can you determine numerically the optimal control for this problem? Or I didn't understand to what extent you can get for a general setup of this type an answer to that question.
The question is with numerical simulation, can I have the optimal control problem?
Yes. Or when can you have it? Or
yeah, actually, we have just the existence of the solution.
Yeah, that's what I thought. Yeah, so I didn't.
Yeah. Just remember what I present you for the beginning. I don't know, but for this problem, which was this problem, I had the uniqueness, and we have the numerical simulations. We have the optimal control problem, and this is the quietly. Okay, this is also reaction convection diffusion equation, and we have some trick, and we reach it. So I have hope. This is just the beginning, but maybe from now, no, we have just the existence of the solution. We have not the uniqueness. Okay, what we do is, so we start from the model. So numerically, what you do is that with Pontryagin optimality condition, this is optimality condition, so you need it, and it gives also a dual problem. So this is the dual problem of these two-state equation, which are anti-diffusive, but well posed because they are not with initial conditions, they are with terminal condition. So you solve this dual equations, you solve the state variables, and the optimality condition of Pontryagin give you a relation between the control variable and the dual variable. So you do this, and after you have to repeat it in order to have the optimal control solution. But without the uniqueness, this is local solutions. Yeah.
I have a So again, going back to this lifting and shifting.
Yes.
So this is, so I'm not a PDE person. So this is kind of the first time, or maybe I heard it 20 years ago somewhere, but not recently. So can you again explain so this is somehow the idea that you can transform something that happens on the boundary to something that happens in the interior. But yes. What is the philosophy, or why is that possible? Or I mean, I believe that it is possible. Okay. I believe you, right? But why is it? Okay. What's the physics there, or what's happening there? And I don't know if this can be answered.
Physically, the control is at the boundary because the phosphorus load enter in the lake at the boundary. So physically, the Dirichlet boundary control problem is realistic. But mathematically, to have the control on the boundary, we cannot reach with this. We cannot have all the results that I have shown you, existence, uniqueness, it's not possible. So there is a trick, which is to build a lifting operator, which has this lifting operator is not unique. For each model, you have a lifting operator, okay? And this lifting operator enables to shift the control from the boundary to the entire PDE. So here, this lifting operator, for this lifting operator, we need, so we look at the control variable, P, and there is a unique solution of P solving this equation. This equation is a type of 8 problem. So it works for our problem, but for other models, this will be another type of problem. And we have this harmonical lifting, which is this elliptic counterpart of 8 problem. And so this lifting operator, which is called R of P, P tilde equals P, enables to remove the P who was here in another formulation of P in the PDEs. But the formulation here, it's divergence VP according to the lifting that we have. With another model, with another lifting, it will not be divergence of VP. It's because we have this model that we have this lifting and that we have this formulation of P. So I don't know.
So you're saying a certain control applied on the boundary somehow is equivalent to some different control in the interior somewhere.
Mathematically,
there's a mapping between the two.
Yes, mathematically.
And both lead, if I link them correctly, to the same solution for the desired.
Yeah, but because
why is that? I mean, is that I'm trying to.
Okay, maybe I was not clear.
I mean, this
in the lifting you have it's like a change of variables. You see that before the model was with S tilde and C and P tilde. With the lifting, we have S, which equals to S tilde minus P, and P, which is the lifting of P tilde. So this is a little change, okay? This is not the exactly same S tilde, this is S. This is a change of variables. It's not change of variables, but kind of with the lifting. So mathematically, yes, this is equivalent. I know this, yeah.
May I add a comment on insist on this a little bit? Just my view. You'd correct me if I'm wrong.
Yeah.
So you have a problem with boundary conditions. Okay. Imagine that you can't solve that exactly. You know the boundary condition, and then you know as the evolution goes, you know the concentration everywhere. Okay. Then if you know that, you can say, okay, I can formulate another problem. But what I do is just put that concentration that I knew because I knew how to solve it, I put in there and I remove it from there. You can always do that, I guess.
Yeah.
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 The problem is that thing must not be easy. That's what I was asking before.
It's not easy.
How you decide how that function is, but it seems that there is a way to do it.
Yeah.
So that's pretty impressive. Yeah. Exactly.
So you tell me that independently of the shape of the line, regarding the shape of the line,
yeah,
if you put the end in a given part,
yes,
is it going to put another end in another part of the line?
Yeah, because
does the same mean it always can be represented as an inclusion independently of the shape of the line?
But there is a flow, huh? Here.
Yeah.
Shape where you have an interest here, it could be a right and goes all the way up there and down there and whatever, and have a kind of shape which might not be convex.
Well, that's the aerodynamics is not in the model. Just the constant V. And
in general, V, which is a function of position. You have these equations that are written in general. Now you have vectors in a given point, and you tell me that there is a lifting operator that no matter what, you can compare this entrance is also distributed on the way.
Yeah. Yes. Yeah.
I think it's independent on the shape of
yeah.
the fact that you can do that.
Yeah.
I guess the lifting operator would depend on that. Depends on where you have that. You have a lifting operator or another, or the operator must depend on the lifting operator must depend on the boundary conditions. Everywhere.
Yeah, but the boundary conditions are P. This is P, the boundary condition.
Yeah.
So it depends on P. Because P is the boundary condition, and that's the problem.
I think
he's not the one. He's the entrance of phosphorus at a given point in the boundary.
Yeah, but you know it.
Exactly. We have to think about it.
Yeah, I'm here for 5 months,
yeah, exactly.
so we can discuss.
Any more questions or comments? Yeah.
Well, this is a bit more general and just curiosity, because you know, in the ocean, so salt water, not fresh water.
Yeah.
There have been now it's forbidden, but they did during a period some decades ago. They did fertilization experiment. That is basically the same. Introducing with iron, but also with phosphorus, for instance, to provoke a bloom, growth of plankton, of phytoplankton, indeed. And so I was just wondering if there's some connection to also that problem. That is, indeed, you want the opposite, no? The aim was to create a lot of biomass, and the more the better. And so I was just thinking if you ever, you know, thought about these kind of problems. That is, in the end, the biology is quite related.
Yeah.
Well.
2 points, and it is mathematical point of view, sorry. But the first point is that here we are in a lake, so this is a bounded domain. In the ocean, this is more difficult, so we have to say that we focus on the parts of the ocean, and for the boundary conditions, more difficult. And the second is that this we can modeling with partial differential equations, but it's not the same that in a lake. Okay, the dynamics in oceans and in lake, this is different type of partial differential equations. I'm not I haven't tried of these equations, but I think this is related, yeah. But more difficult because in the lake you have a bounded domain, so this is more simple, less difficult, but more simple. But yeah.
Thank you very much.
Thank you.